All right, hello and welcome. In this video, we are going to use this parallel RL circuit here and measure the phase angle. The phase angle is a little bit different than the phase lead. Phase lead is what the inductor is doing specifically, so you measure around the inductor with your oscilloscope. The phase angle requires something a little bit different, and especially since it's in this parallel circuit, it requires yet another resistor be added to the circuit because of us working in multisim. So we're going to right-click, place component. We'll grab out any resistor we want there, and that you can find it in the Basics tab, and then go down to Resistors, and you're going to grab out any one of those and place it in our circuit. Once it's on your mouse, you can just drop it onto the line and it'll join into the circuit. We'll close this out. And we want to make this resistor, double-click on it, really small, so 0.001. Right, we want it to have very little impact on the actual resistance and voltage in the circuit there. But we need to be able to measure around something that is linear. And right now we got two parallel components, so we can't really measure around a linear component that's in parallel because we won't see the impact of the inductor, or we'll only see the impact of the inductor. So let's grab out our oscilloscope, again, the fourth one on the sidebar there, or you can go up to your Simulate tab, Instruments, and that's the fourth one down. And here is our 2-channel oscilloscope, and we are going to measure around our source voltage on channel A. So positive lead goes to the top side of our source. That's anywhere above the source, but before this first resistor we just placed. And the second one, the negative lead, is going to go to ground, any ground technically, but we'll put it on the bottom side of our source over here to keep it consistent. Then this channel B here is going to measure around R1, the resistor we just placed in here, and that's going to give us that independent supply to review our full circuit impact, right? The impact of both the resistor and the inductor working together can be seen across this tiny little resistor we just placed in here. Okay, then again, we want to right-click that segment color that's around not the source. You can change any color just as long as one of your channels is a different color so you can visually see the difference there. We can give it a blue color. Then we'll double-click on our oscilloscope and hit play on that. Get a big waveform there, and then we don't even see the blue line, right? Because our resistor is so incredibly small, we're going to end up not seeing that voltage drop being very large. And so we're going to have to scale down that channel B really small so that we can see that resistor. But first, let's do our time base, and we'll stretch this out so we can see the waveform itself. We can stop it there. Our blue waveform is there. It's just on that line. You see that little blue line right next to that white line all the way across. So it's just really small. So we'll go to our channel B, and we'll lower that waveform until we start to see it pop up there, and that's going to be quite a bit because that resistor is so small, right? And after that, we can hit AC on both of these and kind of center them. That way they're around that white line there. They're kind of on top of each other. So again, with sampling, you want to make sure that you measure your values on the white axis line, right where they cross. So we're going to grab our phase, or our probe lines out, and we see that that circle is following the red line, so we can get our frequency measurement in terms of time off of this. We can right-click, go to max, and we can drag this other one over here and tell it to also go to the maximum value, and then that is the distance between the two top peaks, and so that's going to give us our frequency in terms of time, right? That's our period. So we can store that number there and say that we have 667 microseconds. And they're only negative down here. We see a negative right here, 666 down here. And that's because the T2 is in front of the T1. So if we were to put the blue one on the first rise of our waveform where the yellow probe is right now, then that would make that a positive instead of a negative. We just have the probes backwards, which is fine. We just need to know that time isn't ever negative, right? Time can't go backwards, therefore it can't be negative. Okay, so next we want to measure the phase angle. And so that's going to be the difference here. And we do see that it's a little bit different than the last one. The last one was a phase lead. This looks like a phase lag. We see the blue line is actually after the red line. That's what we wanted from this one. So we want to make both of these signals go down to the 0 axis line, and we want to measure them on the front side of this waveform where they're closest together over here. And so we'll just grab our line here and let it run down. We'll right click and go to Y value, and we'll set that to 0. So that it falls on that 0 line. And then you can either double click on your waveform here to transfer the signal, or you can right click, select trace, and go to channel B, and that will move you to the other signal. Now you can see that it's following that one. And so we can right click and go to next Y value there, and we'll put 0 in for that one. And that gives us two zeroed out lines, and now we have a new value down here, 105.9, so we'll round that up to 106. See, that's 106 micro. And we can plug those two values in, right? Because this is our phase difference here, and this is our total time that our signals are rotating through. And so we can plug that into the same equation. We'll put our small number on top, 106. They're both in micro, so we'll leave that off. And divide that by 667. And then we'll multiply that by the number of angles that we have in a full cycle of a circle, right? A full rotation of a circle gives us 360. And that gives us that 57.2. And that's kind of really close to what we expected that to be. Okay, let me know if you have any other questions.